Hi everybody, thanks for coming to this premiere. My name is Nicos and I am a mathematician at the University of Sussex. My research area is probability theory, and one of the many models that I look at is that of queues and traffic, and that's what I'm going to talk to you about tonight. I claim that these are the same as a zombie invasion, and they are. So I really hope you don't mind a few green things popping up in the screen every now and then. Probability originated as a method to understand random events. Nobody can understand everything that will happen, even if we live in a deterministic universe. Therefore, we have to put something to create, to model our uncertainty. One way is gambling. That's one way that people think they will get rich very fast. It's not true. The other way was understanding the future. So the original dice were used for both purposes. Actually, several cultures claim to have invented the dice, at least as early as 2500 BC and maybe as early as 4000 BC. The first die you see here was found in Egypt, so it's actually the oldest one we probably have. But you see how they evolve over time. The second set is something that is used in Dungeons and Dragons, if you guys play any board games. The third one is a spherical die. It's not precisely a sphere, otherwise it wouldn't really sit. But the idea is that it's as smooth as it gets. And then you see that in modern days we have like the weird shaped dice, like those crystal ones that have up to 20 numbers, and then the last one called the deviant dice, which is actually also a fair die. The first one was used to divine the future. The others are relatively modern. So now the real question is, what can we say 4,500 plus years later? Is probability still about gambling? The answer is no, and in fact we can say quite a lot. Uncertainty is all around us, and then we just need to find the correct model. And a bit of time to discuss about probabilistic modeling nowadays. The easiest example that I can think of is the coffee spill. If you spill coffee, what shape does that take? Does it matter on the surface? Is there a way to model that probabilistically? The answer is definitely yes. Now, if you think a coffee spill is a bit too frivolous, even though it isn't, you might want to consider something more serious, like an oil spill. So this is the recent one in Russia. So here the red hue is that of the oil. The oil and the water doesn't mix. The oil moves on the surface of the water, but it's a random movement. There is some deterministic movement using the currents, but local fluctuations remain. What else can we model? Well, for example, look at this petri dish. We can model how microbes grow when there is food or when there isn't food. And then you see these pattern creations here that look like a little tree inside the dish. Is there a way to model that using probability? Again, the answer is yes. The most common one that we are bombarded these days is trends of various random time series. Here I have a stock market. The blue line is the value of the stock. It shows big fluctuations up and down. The green and blue line represent some sort of trend. And the question is, what is the connection between the two? And again, probability can be used to model this. Or we can sort of venture into the field of random geometry or random fractals, like lightning strikes. So in this picture, you see these random curves coming from the clouds towards the Earth. And again, we have a way of modeling that using probabilistic techniques. In this talk in particular, I am interested in something like queues. This is from when the lockdown was eased and IKEA opened in the UK. You can see the queue but if you cannot, let me just point it out. It's here. It's all of this, and it goes, and it goes. And of course, this is in the UK, right? So otherwise, you wouldn't have seen this thing. Here's a much more complicated queue. Traffic. Traffic is a queue, especially when there is a lot of traffic. We are also going to discuss this a bit tonight. But also it has the possibility of sort of overcoming other people if you just enter in their lane. Of course, in the picture here, there is no chance that can happen unless you're crazy. But that's also a form of queue. And the other things that we can model probabilistically is definitely the end of times. Any sort of apocalyptic scenario you have in mind, we can actually do it. So then, what are the questions that are coming out of these models? What can we really answer? Well, for example, in the case of the coffee spill or the oil spill, one important question might be the shape. What is the general shape? I mean, of course, the answer can be blob, but that's not a real shape. So can we say anything about their general behavior? So, for example, if you look at the coffee spill, look how I'm shrinking it, you can see that it sort of fits into some nice ellipse. However, you have some places where it doesn't really reach over there, like there and there and there, and you have some places where it goes out. So we say that those are local fluctuations, and the ellipse is the mean behavior or the law of large numbers. You can also check the oil spill. I'm only focusing in a certain area. Look how that fits. So again, it seems like that the oil spills, especially in the absence of crazy currents, starts to look like a little ellipse or a little circle, and then it's sort of they are stacking them on top of each other to create to sort of understand how they behave in the long run and in an average behavior. In the case of the microbial growth, of course, that's a prettier shape, but can we actually say that you create something that looks like a tree? And the answer is yes. There are several models that are concerned with something like this. In the case of the stock market, what is important is to make money. Trend guarantees that you have an upward trajectory, but in order to make money, you actually need to sell at an appropriate point. And in here, the appropriate point is when it's really up there, right? For the random curves like lightning strikes, when I saw that picture, I only had a very serious question. Why is that last one not going vertically down but is really tilted? And of course, again, our models, when we are dealing with random geodesics, let's say, they can sort of explain why sometimes you have something that is tilted like that. And of course, in the case of queues or traffic or an apocalypse, the question is, when will this nightmare be over? And this is what we're going to discuss today. So let's discuss a bit about some basic queues. But before that, let's discuss a bit the concept. The queues have been characterized as the British national pastime, and here's a picture that can be used as evidence why. But of course, one picture is not enough. So there is this one at the bus stop with no bus. This one with children. This one, an even larger queue. Queues are just so important in our everyday lives that they have captured the imagination of painters, artists, comedians, and writers. Sandy, if you are listening, please say hi. And definitely mathematicians. These are 4 books on queues, and it's just a fraction of what available mathematics is there about them. So let's discuss the most simple queues that are possible that we find. Usually, in the simplest case scenario, there is a server. In this case, let's assume that the server is just an ATM machine. And then people start queuing up at the server. So, for example, here's one guy. So these people we will call the customers. The customers arrive at the queue at some average speed, and they might arrive while there are more people at the queue, and then a queue is formed. or otherwise, they start leaving. But now the service time is actually different than the speed of arrival. So then we have different cases to consider. So for example, if the service speed is much smaller than the arrival speed, then we might encounter a situation like this, which in these days is not even socially distant. Or if the service speed is larger than the arrival speed, it means you are servicing faster than people arrive, and you expect that probably everything will be okay. So here are some questions that we're usually interested when we're dealing with queues. Can we find the average queue length? For example, if that is infinite, it means there is a problem, you need more servers. If we have many queues to choose from, can we find and join the fastest queue? That the answer is no. And then another question is, does it always seem that we picked the wrong queue? And there the answer is yes. So let's complicate things slightly. So let me just describe a horrible, horrible nightmare. This is what we call a first in, first out, FIFO, queues in series or in tandem. At time 0, so when you join the queue, let's say, all the customers are just in front of server 1. Server 1 is this guy here, and this is customer 1, 2, 3, 4. Now, the customers need to actually clear all servers. So this little guy here has something to do with this server here. And after he goes from there, it will join this server over here. And it will join after that this server over here. And then he will wake up this guy and also do his business with that person. Now, after this little guy moves over, this will join the queue in front of server 1. You cannot cut in front of customers and you cannot skip servers. You actually need to go through the whole system, and the service times are random because you never know what is the skill of the employee, what is the task that is necessary to be done, and therefore we can assume that these times are actually random. Okay, so then this is after the first guy jumped. Now this little guy is in front of server 2 and the second customer is in front of server 1, and they're both being simultaneously served. Eventually the system can look like something like this. So server 2 has nobody in front of him, but server 1 is busy. There is a queue in front of server 3 and there is a queue in front of server 4. So the question is, when is the mth customer going to leave this system? So mathematically, when is customer M going to clear server N? Let me just emphasize that this is not just a silly mathematical construct, but actually queues like this exist. For example, you can imagine the situation in a very small airport where you don't have multiple options. You have to queue at check-in, then you have to continue to ticket control, then to passport control, then security, and then finally queue for a coffee, and then go to the gate, and then queue to board the plane. And you have to clear all these, maybe with the exception of coffee, you have to clear all these stages in order, and because you arrive at a certain time, you will never be faster than the people in front of you at this. So one application of these queues in series is how early do you need to be there at the airport in order to board the plane. And in fact, I had a student who did a project some years ago, and the answer came out to be 2.5 hours, which is actually pretty much what they are suggesting we do these days. If you want a more complicated example of these queues in series, you should think of actually the traffic. Now, in my previous slides, I had little particles that were around. From now on, I will just make them like cars. It's a beautiful mini car. So single lane traffic falls into the category of an infinite queue in series. The problem, or actually not the problem, but the thing that matters is that the cars are in order, and because it's single lane, they cannot overtake each other. So they, if somebody's going slowly, they block the other people behind them. But also, what are the servers? The server is just locations on the street. Here's the situation here. I start with a traffic ride on this side over here. Cars are moving this way, and as they move down the line, they cannot sort of overcome each other. So this is like a huge queues in series. If we start from an all blocked initial condition, we might observe some interesting things. For example, this little guy here has no one in front of him. Therefore, he can go fully at the speed limit. And then if for any reason that guy slows down, then this affects this guy over here. But at the beginning of all of this, which is the front of the traffic, you can see that actually there is a lot of spread out cars, and there is enough room to go at almost maximum speed. But then we might want to look somewhere in the middle, and then suddenly we see that there are more cars there. And even if it's imperceptible at the beginning, we might actually have a higher density of traffic. And of course, if we look right at the beginning of this mess, you will see a lot of cars. These people started leaving quite late, so a traffic already started forming, and you see this density here of cars. Now, the thing to keep in mind, the speeds are actually random because we don't know what happens in every car. But the average speed, it's more or less the same. So we want to assume that actually people try to go around the speed limit or whatever the correct average speed is, depending on their situation and weather patterns. But individually, there are fluctuations in that speed. So let's discuss about traffic jam formation, but let's make the situation a bit more complicated, where it's impossible to keep the same average speed everywhere. So I want to split the highway into two regions. Here we have a slow region. That means that the speed there is much less than what the speed is in the fast region. And I have cars, these little balls here, scattered throughout, that they are all moving this way. And I want to understand if I will have a traffic jam, what does traffic jam means in this situation, and without really specifying what is fast and what is slow. I mean, all that matters is that the speed here is larger than the speed here. So this is a very simple setting. It's just a two-phase setting, let's say. But this has been part of my research for almost a decade, if you are interested for more complicated settings, in 2010, I had a paper with my PhD supervisor, Timo Sepalainen, and my mathematical sister, Rohini. And then in 2018, we made an even more complicated setting with my own PhD student, Federico. And now with my new PhD student and my colleague, Enrico, we are actually making an even more complicated setting. I mean, we really want to understand traffic. So how is the traffic jam happening, and what are the parameters that are important? And the behavior actually does not depend on the speed, but it does depend on how many cars you have at the initial time. If you don't have a lot of cars, if you have a low density of cars, as we say, this graph here shows how the car density behaves. In the fast region, it looks constant, nothing changes, but then suddenly there is a shock the moment you enter into the slow region, so when the speed actually needs to reduce, and initially you see traffic over there, and then you start seeing the traffic thinning out, and then being constant again. As time goes by, what will happen is that this line here will become larger and larger and larger, this line here will become more tilted, and then it will become constant again, which means that actually traffic moves forward. So you will never feel traffic until you enter into the slow region. Now, if you have not a few cars, but not a lot of cars. So what we say medium density of cars, and this is very precise in the paper if you are interested. Now we see two things happening. First, we see traffic happening in the slow region, in the fast region as well. So in particular, as time goes by, this shock here, this higher density of cars, will start moving this way. And then eventually traffic will come and hit you. At the same time, this little thinning out that happens here, as time goes by, it will become more and more tilted, but at any time it will be higher traffic than before. So actually, traffic also moves forward. And this is kind of the worst situation. You have traffic going backwards, traffic going forwards, and then something interesting happens. When the speed becomes slow, actually, what you feel is that it goes down the traffic, which is something that is counterintuitive and it's not really obvious just by experience. Now, what happens if you have a high density of cars? In fact, that is also quite natural. What's happening if you are in the slow region here, you don't experience any change in traffic because already you have a lot of cars. But if you are in the fast region, the shock of entering into the slow region will actually move backwards. So in the end, traffic will come this way, and then you will have a lot of traffic in the fast region, but less traffic in the slow region, which is actually quite counterintuitive, but mathematically sound. So how can we prove such statements? I mean, what I said is mathematically sound, meaning that it's provable, irrespective of what conditions I put in the I put on the speeds and so on. So how can we actually prove something like this? And it all begins with a zombie apocalypse. I want to visualize kind of an ideal scenario. So I want to say that my city is square with perfect square blocks, and two of the sides of the square is blocked by mountains. So actually, only two of the sides are available to enter. And I want to emphasize that cities like this exist. And the pictures actually show Salt Lake City, a city that I actually lived in. Salt Lake City is fantastic. It's pure blocks that have precisely a side length of 1/6 of a mile. The streets have the same width, and it's such a grid that instead of standard street names, you have actually grid coordinates. And then what happens is that in such an idyllic city with all these conditions of blocks and mountains on two sides, etc., one day a horde of zombies attacks and they come from the two free sides. Here they are. Now they are attacking. So let me explain how these zombies behave. On the vertical axis, or on this side of the city, I have all these small tiny zombies. Those are smart zombies. On the south side, I have all these big zombies. Those are strong zombies. The numbers you see here, 2, 5, 2, 1, and so on, are just the amount of time each block can survive. So let's say this is a park, so there is no chance that it will survive for more than 0 minutes. But let's say here you have a lot of tanks, so you can survive for 5 hours. However, there is a very serious rule about how these zombies attack. They can only attack if you have a strong zombie below and a smart zombie to the left. So originally, the only square that can be attacked is actually this square here. These squares have don't have zombies on two sides. They only have it from one side. And these squares here, they don't have zombies from any side. But after time 2 passes, this square is really dead. And now zombies of both types are in. The moment that square dies, this square and this square, they can also get infected now, because now there is a strong zombie here and a smart zombie there. So attack here is happening. And here there is a strong zombie and here is a smart zombie, and attack here is happening. And it happens simultaneously. So after time 1 passes, that square is dead. This one has still 4 units to be alive. But then after time 3 passes, this square is dead. And then after one more time passes, then this square dies. And now you see how now that square is under attack, this square is under attack, and this square is under attack. And eventually, zombies keep invading, until eventually every block dies. So this is not a good epidemic, if you want, because there is no hope of survival, but that's what zombies do. And then what you really want to understand is whether do you have time enough for some help to arrive or for some evacuation. So the real difficult, interesting question is, well, when will each block die? And the answer is a random variable called the last passage time. Usually the symbol for it is GMN. I don't think I'm going to use it, but just in case you ever see it in front of you. The answer is that the square NM will die precisely as long as it takes customer M to jump over server N in the original queues in series model. And this is really surprising, but here's how it comes out to be. On the left, you see my little customers. They are 1, 2, 3, 4, 5. Now, every time customer 1 takes a jump, I will make a square here orange on the first row. Whenever customer 2 jumps, I will make a square here orange on the second row. And whenever customer 3 jumps, I will make a square on the fourth row orange. So let's see how this goes. First, the first guy jumped, and now on the first row, the first square is orange. It jumps again, so now I fill one more square on the first row. Now the second guy jumped, and I filled the first square of the second row. The third guy, so that means I fill a square on the third row. The fourth guy, so I go on the fourth row. Now the second guy again. Now the first guy, and so on. So what you see is that what we call a coupling, that one model actually is the same as a different model. It shows how zombies move versus how particles move, and they are both the same thing. So here's just how the square looks colored after I have 300 particles jumping, and on the second picture here it's when I have 1800 particles jumping. And this, what you see with these curves here, these little colors, it just tells you where the zombies are at a given time. So let's say at time 1800 the zombies are below this line here, so it's all the blues. So as usual with math, if you have an idea that works for one case, you really try to make it work for much more complicated cases, because ideas don't come cheap. So far all I talked about was really just single lane highway traffic. So now I want to go to a much more complicated setting where I have a road network, and I have this tree of roads, as you see in the picture. Now, suppose that you have traffic at the initial road segment, and you are really right at the end of that traffic, right over there. And now you want to navigate this network and try and move around until you reach your destination or so. So can we say anything about how the traffic in this case evolves, where now we have a tree rather than a single line? And the answer is yes. This is joint work with my collaborators from the Technical University of Munich, Nina and Dominic. And this is actually a very new result, whatever I'm going to say now. It only came out very recently, so it's really fresh out of the oven. So what's the first thing we can say? Well, a natural question is, you are in the middle of traffic at the beginning, how many exits do you need to encounter in order to feel that traffic thinned out? So we call this the disentanglement theorem. If you look at this picture here, while there are many cars on the street, each one of them is going on a different road. So they're not sort of blocking each other. Okay, this guy may be blocked, but not much. So for example, this doesn't block that one, these don't block each other, and so on. So we call it disentanglement in the sense that the first 10 cars now don't have anything to do with each other, and therefore they can feel that the traffic went down. So what is the answer? Well, under some assumptions on speed limits, because now speed limits become important, and how often you find an exit, so also the stretch of road is important, and also which destinations are desirable. Like, let's assume that not everybody is going to London. Then with about 1,000 cars in front of you, you need less than 10 exits to feel that there is no traffic. In other words, we have that if you have n cars, then you have about log n exits for complete disentanglement. Which is nice because you sort of expect that if the road has a lot of exits, you should be able to see less traffic as you go along. The problem is that it's not always true, depending which destinations are desirable or not. But we have the theorem that says in that case also what's happening. The worst thing that we might want to worry about is, when do you have a total blockage? When do you see a situation like this? A friend of mine said that this is precisely what M25 looks like. I wouldn't know, I don't drive, but I believe him. So the answer in this case for total blockage is that it again depends on car speeds and speed limits, as it should be, and also how many cars enter the system, as it should be. So this is a hint that mathematics works. Like, what we know from our standard experience should be what we see after we prove a theorem. And in this case here, we actually have conditions that directly lead you to this kind of blockage. So if those conditions are satisfied, and you can check easily if you see a roadmap and you ask Google what's going on, then you have a total blockage, and that's never good. We can also find conditions for near empty roads, i.e., if we are able to go at maximum available speed. This is when there is not too much traffic, even though you might start with a lot of traffic. And again, the answer here depends on car speed, speed limits, how fast cars enter the system. However, there is an added benefit when we try to understand this particular question, that we may be able to focus in a certain area, and we can actually understand what is the car density in that particular area. And as you see here, is less than the one above. So then the question is, can we, I mean, if somebody asks me what's happening in my area, can you tell me the car density, knowing that everybody left, let's say, from Woodstock, then the answer is yes, it's possible. Finally, of course, the question when we are going somewhere is, will we reach there on time? How long will it take to reach? Can we avoid traffic? And the answer is that yes, we can actually say the worst case scenario when we will arrive at our destination. And here, in order to get something like this, we actually use the little zombies to find first where we disentangle. That takes up to a certain time. And after we disentangle, where there is no traffic, nothing in front of us, so we can go at maximum speed. And then we can actually accurately compute distances and the time that it takes to reach there. Now, with this, I want to thank you all. Thank you for coming to this premiere. And I would like to remind you that now there is a question session that you can click the link below to reach. Thank you very much for your attention.
Well, we hope you enjoyed this video. Once again, I've got to ask, if you did enjoy it, please give the video a like and subscribe to our channel to see our future updates. If you're interested in the future talks we've got coming up, do visit our website at bit.ly/Sussex Universe. And remember, if you're watching live, the live Q&A starts now at the Zoom link in the description down below.